Okay, thank you for the invitation. It's really fun that I can talk with you guys from here since I cannot travel. I will present today a paper with my co-author Eyal Ert, Ori Plonsky, and Yafim Roth. But I would like to start with a personal story that demonstrates that when I was young, I was even, let's see if I can, something more here. Yeah, that when I was young, I was even less bright than I am today. When I arrived to the Technion as a young faculty member, I got my PhD in psychology and I started teaching engineering students. It was very important to me to show them that psychology is a serious discipline and also to try to encourage them to read the textbook. In effort to achieve both goals, I decided to build on two of the most robust phenomena that I taught, that I cover in my course in Introduction to Psychology. The first one was the observation that many people buy lotteries. It's easy to see that many people buy lotteries, and Kalman Tversky demonstrated very elegantly in the research, where they ask people to choose between 5 for sure and 5,000 with probability 1 in 1,000, and most people prefer the 5,000 with probability 1 in 1,000. So they behave as if they like lotteries, and we know this is a real phenomenon. The second phenomena that I thought is really important is a partial reinforcement extinction effect. The observation that different animals, from rabbit to human, exhibit this phenomena that if they learn something from partial reinforcement, the learned behavior is more robust, doesn't change. So building on these two robust observations that I cover in class, I come up with the following idea to encourage students to read. I basically told them that we will start that I encourage them to read the book chapter before each class. And I will start each class by randomly selecting one student and ask him or her a question from the textbook. And if he or she will answer correctly, they'll get 2 points to bonus to their final score. This idea works like magic. In the first week, students got really excited. I get the library of our faculty come to me and say, what did you did? This is amazing. I never saw, I'm here in the Technion now for 30 years. I've never seen students getting to the library more than a week before the exam. They actually read the textbook. You really are a good motivator. I was very proud of myself. In fact, even the dean noticed that and people were really excited. So that was good in the first week, but the effect was not as good in the second week. In the second week, I asked a student a question and she answered in a way that was not clear that she will actually read the book. I still gave her a point. And the other student got really upset that I randomly divine points. People stopped reading, and all that I left with was a frustration that I use an unfair method. So I tried to illustrate that I can predict, that I can use basic idea in psychology to motivate people, and I really demonstrated the opposite. I now think that my failure suggests that I did not know enough about the condition of two of the textbook phenomena that I taught. Much of my recent research, and when I mean recent research, I mean research in the last 25 years, tries to correct this problem. What I'm trying to do is to try to clarify the condition under which the robust phenomena in psychology occurs, and also when they do not occur. Part of our research, one of the clearest indication of our research that you can explain much of this inconsistency and improve much of the boundary condition by distinguishing between decision from description and decision from experience. Decision from description are the phenomena, are situation like the problem studied by Kalman Tversky, when subject receive a description of the choice problem. And decision from experience we call to situation what happened after you get experience. Our results show large gap between experience and description. The clearest difference involve the effect of rare outcome. Here is an experiment from the 2017 paper. In this experiment, subjects were asked to face the problem, choice task between 2 for sure, the pair for in shekels, and they were paid for one randomly selected trial, 2 for sure, or a lottery that pay 101 in probability 1 in 100, one otherwise. Expected value of the lottery is also 2, like the sure outcome. Our results, and basically the subject faced this gamble repeatedly for 25 trials and start getting feedback only after the 6 trials. Our results show that in the first 5 trials, before they got feedback, they selected the lottery about 55% of the time. That is more than 50% of the time, in line with the prediction of Kahneman, of the results of Kahneman-Tversky. However, once they start getting feedback, proportion of selecting the lottery went down almost immediately. After 2 or 3 trials with feedback, the choice rate went down to 42%. So initially, subject behave as if the overweight rare event, but after a few trials, they start behaving as if they exhibit the opposite deviation from maximization. The current paper extend this research by trying to clarify the boundary of 6 deviation from maximization documented when people get experience. To clarify the impact of experience, our analysis focused on a very simple experimental task that we called it the clicking paradigm, the full feedback clicking paradigm. What you see on the screen is an exact instruction that the subject get when they get to a typical experiment. Basically, the subject is told, the current experiment includes many trials. Your task in each trial is to click on one of the 2 keys presented on the screen. Each click will be followed by a presentation of the keys payoff. And your payoff for the trial is a payoff of the selected key. For example, if the subject press right in the first trial, he gets a feedback. In this example, you selected right, your payoff in this trial is 1. Had you selected left, we also give him full feedback and basically said, had you selected left, your payoff would be 0. This was trial number 1, and then trial number 2, suppose the subject select again right, and he get again feedback like that. In this example, again, you selected right, your payoff in this trial is 1. Again, had you selected left, you would get 0. Notice that this paradigm is simpler than other paradigm used to study decision from experience, in the sense that it's that other paradigm involve confounding between exploration and the impact of experience. In this case, exploration, it minimizes the importance of exploration because the information available to the subject does not depend on their choice. So it's allow relatively clear evaluation of the way people react to experience. Well, I will present several experiments using this paradigm in this talk. All of them were run for 100 trials. Some of them run in the lab, some of them run in MTurk, and we don't get big difference between Technion student and MTurk workers. Some of them, all of them, the point were converted to money. We use different conversion method, and we don't find big difference between the conversion method, so I will not discuss it further. I will challenge you to try to predict the results of our experiment. We will do that in using the chat. My co-author Yafim will here's Yafim if you see him. Will try to record the results. So the person who will win most correct answers will gain a prize. The first prize will be a free copy of our electronic copy of our paper. Third prize will be a weekend in Haifa. Okay. I will let the winner decide which prize he prefers. Okay, so let's see. Oh, by the way, so the person who will answer most correct answer will be the winner. And if there will be 2 the same correct answer, Yafim will determine the final winner based on speed. So try to be quick. Here is the first question for you. So this is a paradigm I showed you before. Subject has to select between 2 keys. And there is 2 problems in this experiment that I would want you to predict what will happen. The dark problem, the subject, 1 key, we'll call it A, gives 0 for sure. And option B lead to a loss of 10 in 10% of the time, and plus 1 otherwise. That is the expected value of selecting B is minus 0.1. The payoff in this experiment were in shekels. This was run in the Technion. And option and the light problem. So there's 2 conditions: the dark and the light. In the light condition, option A gave 0 for sure, but this time it's just like the dark problem. But this time, option B gave plus plus 10 with probability 10%, minus 1 otherwise. So the expected value of option B was plus 0.1. So those of you who want to guess, we'll give you now, let's say 10 seconds. If you have not guessed yet there, what do you think will be the choice rate? Either option A, 22, both option 20, option B. You have to guess the B rate. So the guess, the possible guess are 20-20, 80-20, more B in the dark problem than in the light problem. That is the opposite of expected value maximization, or the opposite, more B in the light problem where B maximize expected value and A no. Okay, do we have some answer? Yafim, can I move to the next question? I think yes, right?
Yes, we have some answers, actually, okay. Quite a few.
Okay, here are the results. You see here that the correct answer was C. So basically, in both problems, subject deviate from maximization. And here you see the learning curve, the 100 trial. By the way, in most of these experiments, learning curve tend to be relatively flat. And basically what you see here is that in the dark problem where the expected value is negative, subjects start selecting option B about 70% of the time. And with experiment after 100 tries, they go down to 60%. In the light problem, when the expected value from B is positive, they start selecting it only 20. And after 100 tries, they go up to 30%. So these are the results of this experiment. These results appear to suggest that the subject behave as if they underweight a rare event. Hopefully, we get many correct answers here, Yafim.
Yeah, I think about 7 to 10 correct answers out of 12 or 15 submissions. So okay. Quite a lot of people.
Okay, so not everybody gets it right. Let's see if you guys get better during this talk. Here is question number 2. Now the subject have to select between the two problems. Both of them involve a choice between a prospect that provide 12 for sure and another prospect that paid 10 plus another thing that basically give an expected value of 1. So basically they have to select between 12 for sure or a prospect that give 11. But in the dark problem, the option B give 10 plus the lotteries that give either 10 with probability 0.1, 0 otherwise. So expected value is 11. In the light problem, option B basically give 11 for sure. Now the option for you to answer is that B is selected only 20% of the time, 80% of the time, or option C, B is selected less in the dark problem, and option C said no, B will be selected more in the dark problem. So let's see if we have some guesses. Yafim, do we have guesses already?
Yes, we have actually quite a few.
Okay, some people want to come to Haifa. That's nice. Okay, so let's see the results. And here's the results. Just mention this way. Okay, so the results suggest that in this case, option B is selected more in the dark problem when he provides a lottery. Notice that this result suggests underweighting of rare events, the opposite of the Kahneman-Tversky result. This result suggests a prospect theory-like overweighting of rare events. That is, they behave as if this lottery, this 10 with probability 0.1, is more attractive than this 1 for sure. Okay, so we get both underweighting of rare event in this problem and also some indication for overweighting of rare event. Okay, our goal in the end of this talk will be to come up with a model that can explain all these results. But before we talk about the model, I want to show you some more results. What proportion of people got this one correct, Yafim?
I think about 80%.
Okay, you guys are getting better. Now let's look at this problem here. In this problem, we have 3 options. Option A, let's start with option C. Option C is a status quo, you get 0 for sure. Option B give you either 4, +4, or -4 equal probability. And option A give you +8 or -8 with equal probability. notice that the correlation between the pair of the two risky prospects, the two red prospects, is -1. When A give +8, B give -4. Now my question for you is, what was, basically the question is, what was B rate and the C rate? The C rate, of course, is more interesting because this is a status quo. So what do you think was the C rate? 15%, 34%, 35%, 60, or 90? Please answer in chat, and in a minute we will ask Yafim what was the proportion of people that answered correctly. You get some answer, Yafim?
Yeah, we have 4 answers, 5, 6, 7.
Okay, in 8 we're gonna stop.
8, 9, I think even about 45% correct answers.
Okay, so the results here is that subjects really don't like the status quo. Proportion of selecting the status quo here is only 15%. And this is how the learning curve looks. By the way, the results I show you is, of course, in block of 20 tries. So you don't see the very first try. Of course, in the first tries, they know nothing. They select it randomly. But very quick, they learn that the green is not very attractive. This result suggests gain seeking. Subjects don't like the status quo. It's, of course, a reversal of the status quo effect, and also could be decided as a reversal of loss aversion bias captured by prospective. Although I'm not sure if prospect theory had a clear, if there are people in the audience who like prospect theory, they might tell me that prospect theory is not, doesn't have really prediction for more than 2 outcomes. But it's against the way people generalize prospect theory. Here's another question for you. Very similar to the previous one, but we now change the correlation between the two risky prospects. Now they are positively correlated. When A give +8, B give +4. C still gives 0 for sure. Now we also change it a little bit so the risky lottery are more attractive in terms of expected value. The question for you, basically I want you to compare option B and option C. So the question, was it B exactly like what happened before, or maybe it will be reversed, or maybe you get even much more sunk cost effect in this setting. We have some guess, Yafim?
Only one of them.
Okay, and this guy is, this person is accurate?
I will not tell you yet.
Okay,
You'll have to wait for a few more seconds.
Okay, let's try it until we have 5 answers.
Yeah, we already have 5 answers. I think only, if I'm correct, only one person got right this question.
This is a correct answer.
Yeah.
So the correct answer is that in this setting.
No, already 2 people. Yeah, sorry.
Got it accurate. Very good. So basically in this problem, it's of course more tricky. In this problem, we get, I guess most of you realize that in this case, we get more status quo effect. So proportion of people selecting the comparison of B and C suggests some indication of loss aversion. That is, although B has higher expected value than C, people select C 35% of the time, yet they select option A, of course, even more. These are the results. I have to admit that I could not predict myself the difference, why option A is so popular, but these are the results. Okay, so Yafim said 2 people got this one correct. Okay, so
yes.
Okay, we are moving for a different problem. In this case, we have a trivial choice between 0 for sure and 1 for sure. And again, the light problem is again 0 for sure, but now the option B that has expected value of 1, just like here, now have high variability. What do you think happened to the maximization rate? In which problem we have higher maximization? So you have to guess whether this pair variability had little effect, and we get basically the same maximization here, or maybe pair variability actually increase maximization or decrease it. What is our choice rate? How many people answered, Yafim?
5 or 6. Actually, people have very good intuition about this problem.
Okay, so let's stop it because you guys we don't want too many correct answers. So in this case, we get a certainty effect. Basically, when the high expected value option is certain, then you get high maximization rate. Basically, we don't get this experiment we run in the lab. We typically don't get more than 90% maximization rate in those experiments. So this is the highest we can get, more or less. But when you add variability, choice rate move toward random choice. Okay, let's look at another question of the same sort. This one is a little bit more complex. We still have here the dark problem, some pair of some safe prospect versus a gamble. And now we take, as a top problem, we take the option B that was safe here. Now we replace it with a gamble with the same expected value. So the question, what will happen with the maximization rate in this task? Okay, so I revealed the answer by mistake. So you get some. So that was...
Yeah, but I'm not sure if I got them before you revealed it or after.
Okay, so let's record that. Thank for you. Okay, so in this case we get the opposite. In this case, option B is less popular when it's provided, although it has higher expected value, much higher than option B, A. But in this case, when option B provide 1.35 for sure, it's selected only 50% of the time. And when you add variability to option B, its choice rate goes up to 70%. So here we get a certainty effect, and here we get a reverse certainty effect. Okay, here's another question. This one is a little bit more complex, but I will explain it. Here you can think about it as a simulation of a real-life problem in which you are a policymaker, and your task is to reduce the reckless rate. So basically, subject have to select between a safe prospect that give 1.35 for sure, and two risky prospects with lower expected value that can lead to an accident. We're going to think about the loss of 20 as a simulation of an accident. And when we run this experiment, the dark problem, proportion of accident was 2.1%. So subjects selected option B quite often. Option B lead to an accident only in 3% of the time, but selected quite often, so the accident rate was 2.1. Now, suppose that you are a policymaker and you want to reduce this accident rate, and you decided to use tax or a fine to reduce the tendency of people to select B. Basically, you reduce the pair from B by 0.4. So instead of having 1.6 as a pair of B, now the pair from B become 1.2. What do you think will happen to the accident rate? Will not change, will reduce to about half, or will go down to 0, or will actually go up? We get some guesses. Yes.
While waiting answers, we have one clarification question.
Sure.
It says, what are the sample size in the various studies? Maybe you can add.
Yeah, it's between 120 and 45, I think. So all these results are pretty robust. Yefim, do we have some answer?
Yeah, we have about 7 to 8 answers. And
how
actually,
many of them are correct?
Only one, I think, is correct. Yeah.
Okay. So in this case, taxing the most attractive risky prospect actually increases the accident rate. And this is you could think about it an example of this fine is a price effect by Gnisi and Rostaccini. And the reason why this is happening is that when you make option B less attractive, it moves people to option C, which is a really stupid option that lead to an accident in 6% of the time. And not everybody moving, but enough people move, so it's become a negative effect. So basically, we see here a fine is a price effect in this setting. Here is another question. Now, you have in the dark problem, you have a very attractive option that give 100 with probability, I meant to write 2%, or one otherwise, expected value of 2.98, and option B that gives 0 for sure. So now think about the government. You say, well, everybody going to select option A. In fact, they select it 91% of the time. Maybe I can gain some money by reduce the attractiveness of option A and get some more taxes. Let's say that option A is so attractive after when there is a small tax. Now we can increase the tax and still gain a lot of money for the government for say, to do good thing for the public. So in the light problem, they reduce the option A, the pair from A from 2.8, expected value from 2.98, we move it down to 0.98. What do you think will be the choice rate of option A? That is, what will be the maximization rate in this setting? 95% actually will increase the maximization rate because now subject notice there is some, the losses will give them increased attention, will have no effect or reduce it. Do you have some guesses, Yafim?
Yeah, we have a few correct answers now, or already more than a few.
Okay, very good.
60%.
So the correct answer is 30%. In this case, where here the people behave as if the fine is a price, here they behave as if this taxation is really negative, although it's much more negative than it really is. In fact, it didn't change the optimal strategy, but it reduced the maximization rate from 91% to 30%. Okay, let's see how much time we have. I have two more phenomena. Maybe I will do this one. Okay, in this task, now we're going to study what happened when you are interested in the comparison of option A and B. Option A and B are the same in the dark problem and in the light problem. The only difference is option C. In this dark problem, option A dominates option C. In the light problem, option C prime is dominated by option B. Now the question for you is when option B was selected more, in the dark, when A dominates the third option, or in the light problem where B was a dominating option. What do you think happens here? So option C basically option D actually is basically suggests that we'll have a decoy effect, that B will be more popular when it dominates option C, and option C said we'll have a reverse decoy effect. Option A and B will have no decoy effect. The third option will have no effect. We have some answer, Yafim?
Yeah, we have 2 correct answers out of 5. Actually, already 3 out of 6.
Okay, so here we get a reverse decoy effect. This is a replication of a study by Spector Tales that just appeared in Psych Review. The next problem here, I see I have a typo, so I cannot really ask a question about it. In this problem, here we have the original decoy effect. In this pair of problem, B is more attractive when it's dominates C. So we get both reverse decoy effect and original decoy effect. And again, I will skip the question for the next thing because I see my time is running. So basically what you saw here is a decoy effect, a reverse decoy effect, replication of Spector tail, and the original decoy effect. And here what we see is a reverse compromise effect, again, replication of Spector tail, that show basically what we see here, that B is more popular when it's not a compromise, and it's less popular when it is a compromise. And here we get the reverse, so this is a reverse decoy effect, and in the light problem, we get the original decoy effect. Okay, so basically what I've showed, I've showed, the results that I've showed you, is that we get, basically replicated 6 phenomena, deviation from maximization that observe in basic study of decision from experience in previous studies. But in our study, we could replicate these results, those are replicable, but we also find condition under which these phenomena are reversed. We get deviation in the opposite direction. And the question is, how do we explain the coexistence of the fact that we have 6 phenomena and they are going in, they're actually 6 pairs. We get each one of these phenomena, we also get the opposite. So, you know, economists, my economist friend, David Schneider, like to say, you psychologists, sometimes you get deviation in one direction, sometimes you get deviation in the opposite direction. So on average, we can ignore you. Of course, it's a joke. The question, can we actually predict under which situation you get a different deviation? In our effort to predict this, the direction of this deviation, focus on what we call the reliance on small sample hypothesis. And I will try now to present this hypothesis to you. And before I present it, I want to say that there is 4 good reasons why we like this hypothesis so much. It has 4 attractive features. First, this hypothesis is very simple. So very simple abstraction of this hypothesis can capture all the 6 deviations, the known 6 deviations from maximization that we replicated. That is the results I presented in the top part of each of the slides before. And this simple abstraction basically assumes a sample of 5. Basically, what this model says that the subject, now your number, try number 71, the subject recall 5 past experience. For example, try number 17, 23, 24, 60, and 64, and check which prospect had higher average in this trial and select that prospect. This is basically what the model says. So this very simple model can capture all the 6 known replication from deviation from maximization that I've presented. More interestingly, the same hypothesis actually predict the reversal of this phenomena. So the phenomena that I presented, the experiments that I presented in the lower part of the previous slides, were designed based on this hypothesis. We designed this experiment because we knew that this hypothesis predict reversal of the top phenomena. Another good reason for our interest for this hypothesis is that it captures, we organize 4 big choice prediction competition, challenging people to predict behavior, to send us model to predict behavior in decision from experience. In all 4 competitions, the best model basically were a different quantification of the reliance on small sample hypothesis. And the difference between the model were not about this hypothesis, but it was about each one of this competition focus gave subject different prior information. So all the addition were about the prior information. The 4th and most important reason for me is the fact that this hypothesis is not just one random cognitive process. It's actually a summary of multiple reasonable cognitive processes. Reliance of small sample is predicted if subjects are lazy or have cognitive limitation, but it also predicted if subjects are sophisticated and they try to maximize, to approximate the optimal Bayesian strategy in a dynamic world. To see that, think about the following thought experiments. Actually, those of you who want can put their answer here. You can put your answer here but there will not be competition on this one. We just want to see your intuition. In this experiment, this is a thought experiment in which in each trial you have to select between top and bottom. And it's include, and now we are now in trial number 16. You have to select in trial 16 between top and bottom. And here are the results of the first 15 trials. Basically what you see is bottom always pays 0 and top paid -1, -1, -1, +2, and so forth. So I ask you, what would you do in trial 16, assuming that you have not taught statistics for too long? We get some answer, Yafim? But if we do not, you have some?
Yeah.
Okay, so if you guys are similar to our subject, what you do?
Yes, they are similar.
They are similar. So the most intelligent people, as I said, assuming they have not taught statistics for too long, select top in trial 16. Notice that this choice amounts or imply that basically the subject say, well, I had 15 trials already in this task, and I noticed the expected value from top is negative. Nevertheless, I feel that I should select top. Why? Because I feel that I should not use all past trials. Only 3 trials are relevant here. Trial number 4, trial number 8, and trial number 12. Why? Because these trials are similar to trial number 16 in the sense that they come after 3 trials with 3 minuses. In the psych review paper, Plonsky et al. Show that this logics that I just presented that our subject exhibit approximates the optimal Bayesian strategy in this task. So it could be that subject behaves if they rely on small sample, not because they are limited or stupid or lazy, but because they are sophisticated. In fact, I think it's very hard to think about a cognitive process that will not imply reliance on small samples in this task. So basically, they show, as I said already, a very simple abstraction of the reliance on small sample capture all the results I've shown you so far. But when we try to improve upon it, we saw you can improve it by adding some stochastic choice rule and also assuming some sensitivity, low sensitivity to the average pair. Just to show you how well you could predict with this very simple model, here are some of the results. So here you see the results I show you for the first experiment, and this is a prediction of the reliance on small sample model. I just want to go the intuition why the small sample model in the dark problem selects the low expected value 60% of the time. To do that, think about the model as a simpler variant that assumes that the subject relies on sample of 5 experience. If they rely on 5 experience, they will select bottom, they will select B, unless the sample include a minus 10 outcome. Because if it doesn't include the minus 10, the average pair in the sample is +1. If it includes a minus 10, the average pair in the sample is negative. The probability of having the minus 10 in this example is 0.9 to the 5. And that is the probability of not having it is 0.59. So they selected it about 0.59% of the time. And I'll just show you that why the reliance on small sample imply overweighting of error event here, because the reliance on small sample will never select the low expected value when there's no variability, because in each trial 12 is more than 11 when you don't have variability. But if there is variability in some trials, small proportion, the subject actually sample a trial in which he wants a +10 and then he selects. And this is our explanation for why people buy lotteries. Sometimes they feel lucky because a good outcome come up in their sample. The small sample hypothesis also predicts the reverse loss aversion pattern here, and also the original loss aversion pattern here. It also predicts the certainty effect and the reverse certainty effect, and also predict the observation that taxation can backfire, and also that sometimes taxation is too extreme. So basically, this very simple model can reproduce all the 6 pair of contradicting results that I've presented to you. Okay, hopefully I convince you that this very simple model is useful, but maybe some of you say, okay, but who cares about this stupid clicking paradigm? So we have a simple model that capture behavior in this clicking paradigm, but we care more about real life phenomena. I think that this clicking paradigm is simple, but I would like to argue that it's not too simple in the sense that it's replicate, in this paradigm, we replicate some real important phenomena. And the more interesting is the observation that this phenomena that we were basically able to replicate, or at least demonstrate sufficient condition to, in previous research were explained by very different hypotheses. For example, the fact that people buy Texan while drive can explain with reliance on small samples, because most of the time that I Texan drive, nothing happened to me. I once got fined, but I never killed myself. But the common explanation for that is some addiction. People are addiction to their smartphone or something. They might be addicted, but there's also a simpler explanation. The fact that people buy lottery, the common explanation is that it's reflect reverse S-shaped function by prospect theory. But this phenomena does not explain why most of us don't buy lottery very often. On the contrary, the reliance on small sample hypothesis explains this phenomenon. The fact that most people do not invest in index fund but prefer to invest in individual stock is explained by in the finance literature by overconfidence. But notice that this phenomena also can be explained by reliance on small samples. The observation that people underinvest in the stock is the most popular explanation is myopic loss aversion. But as I show you, this phenomena can also be the product of reliance on small sample. Certainty effect explained by risk aversion in the gain domain. Reverse certainty explained by variability seeking. Again, both phenomena can be captured by reliance on small sample. Finally, the price effect explained by crowding out of intrinsic motivation, but can also explained by our story. Reverse decoy explained by similarity, induced subjective reinforcement, and so forth. What I would like to argue that we have many interesting explanations for each one of these phenomena, and for some reason the literature ignores the fact that all these phenomena can be captured by the very simple reliance on small sample hypothesis. And once you accept the reliance on small sample hypothesis, you can not only explain the phenomena, you can also predict when the phenomena happens and when it's reversed. So as I said already, the main advantage of the current explanation, I'm not saying that the other factor is not important, but maybe the reliance on small sample is an important driver of this real phenomena. And if this is the case, we can explain the conditions that have this effect. I want to discuss three practical applications. The first one is my stupidity from the 90s. So obviously I did not understand the experience description gap, nor did I understand that following experience, people start behaving as if they're underweight rare event. So I now would avoid my mistake. Hopefully you guys did not exhibit my mistake. However, you know, I'm participate in some of the some of the meeting of the Israeli Insight team, which is basically run by Dan Ariely. And Dan himself understand my results, but some of the other workers in this field always come with the idea, let's increase some behavior by using lotteries, because we know that people love lotteries. I always have to remind them of this result, but they tend to forget it every time. Nevertheless, lottery will be effective. If you want to increase the probability of people selecting something from 10% to 20%, lottery might be effective. But if you want to increase it above 50%, this is not the right way to do it. A more interesting question that now many people think about it is about teaching in Zoom. So the fact that Zoom works was a surprise to many people, including myself. But later we realized that students really hate Zoom. So many students, not all of them, hate Zoom, including my daughters. They said they cannot concentrate in Zoom. And the question why? And I think that the result I've shown you provide one explanation. I think that what happened in real class, that you sit in class and every time you want to look at your phone, the teacher look at you in a funny way and you continue looking. So you get negative punishment every time you do the wrong thing. Not every time, but sometimes enough time you get it. When you're in Zoom, and it's boring, you stop listening. So we have to find something else to get attention. This is why in this talk I tried so hard, and Yafim helped me out by presenting these quizzes. And I think that, of course, many of you I know you're already doing it, but I think some people don't do it. Definitely some of the teachers in my daughter class don't do it. To do it well in Zoom, we have to ask questions all the time for students because basically you sit in a talk and most of the time it's boring. Once in a while, the professor or the teacher will say something interesting, but this is very rare event and people underweight rare event. For that reason, I think the quizzes in Zoom are really important. The third example, a more important one, is the reaction to COVID-19. And basically our research suggests that there are gonna be two reactions. Some people will behave as if it won't happen to me, where others will panic. President Trump maybe read prospect theory, probably not. He thought that had he informed Americans in January 2020 of the risk associated with COVID-19, they will panic and the stock market will crash. For that reason, he decided to tell them, no, it's not a problem, just drink some Economica and everything will be good. So he behaves as if he believes prospect theory. Our analysis suggests that panic is indeed the problem, but it won't happen to me is the larger problem. And in order to do that, we have to enforce. It's not enough to tell people there is a problem, because people behave as if it won't happen to me. In fact, look at me. I'm hanging around and I still didn't get corona. So maybe I have the whatever it takes to fight it. So I feel pretty safe now. And we can solve this problem like it was done in China by imposing high costs on people that do not want to use a contact tracing application, for example. So in China, they basically solved the problem or eliminated it or reduced it by forcing people to use contact tracing applications. So when they see a change, they can break it very quickly. It's not easy to do in the West because we don't want to force people, but basically the result I present to you suggests that it can also be done in a gentle way. One way to do it, for example, is try to have a contact tracing application that is more similar to Waze or to Google Maps. That is to have an application that if you use it, helps you save time. So we propose in a paper with Yafim and Uri Plonsky, we propose that you can solve this problem, but for example, by letting people the option to get into public places in two ways, either by showing working application or by filling some forms that will take 5 minutes. And basically, we suggest that many people, enough people in order to break chain, will install application if it solves in 5 minutes every day or two. This is our hypothesis, and we think based on looking at the popularity of application like Waze, that might work. Okay, I would like to discuss an even wider question. Why we psychologists really love so much situation-specific explanation and pay little attention to phenomena like the reliance of small samples that can explain many phenomena. I think there's two problems that lead to that, two difficulties that lead us to this tendency. The main one is our fascination by the rationality assumption. Because from historical reason, research in decision-making started by challenging the rationality assumption, we focus on decision from description because to show a clear violation of rationality, it's important to study decision from description. Because in decision from experience, almost every behavior can be justified as rational under certain assumption. And because we study decision from description, basically our research, we pay little attention to the effect of experience. So basically mainstream research in behavioral economics build on research of decision from description and then try to predict what happened in decision from experience. And what happened is exactly what happened to me in the 90s. We have nice prediction that works about 50% of the time. Another reason for the focus on simple models on narrow situation is the fact that many people, especially cognitive psychologists, think that if you propose a model, it has to be, the model have to assume that you know that it's include a well-specified description of the underlying process. If it is under this assumption, you can actually estimate the parameter for each individual in a very elegant way. However, this is a crazy assumption. Why would you believe that you know the actual process? And basically, I think if you think to justify this assumption that you know the process, people focus on a very simple experiment. This helps you estimate parameter, but it's really impair prediction of behavior. I think, and when I talk with psychologists, many times they say, well, you are interested in prediction, but we're interested in understanding. I disagree. I think if you cannot predict, you do not understand. I learned that in the 90s. And what you understand, if you estimate prospect theory parameter, for example, for some problem, you only understand what was the parameter that best fit your results. But do you understand where your results is going to happen? I don't think so. So here is my summary. And I think we will have time for questions. Maybe not so much time.
Basically, we have the winners.
Huh?
And we have the winners.
Oh, the winner, okay. So behavior economics try to improve upon rational economic theory by capturing robust deviation from rational choice. This is very interesting research, but it has an important shortcoming. The main shortcoming is that it shed limited light on the conditions that trigger contradicting deviations. Part of the contradiction reflects the description experience gap. Yet the description experience gap is incomplete. For example, it cannot explain why people buy lotteries. I try to convince you, the counter-analysis demonstrate that a simple abstraction of the reliance on small sample hypothesis resolves the 6 pair of contradiction we examined. While the deviation from rational choice are situation-specific, it is not necessary to assume situation-specific biases. Very simple model can help predict behavior. That was basically my story.